Although the ArrayList class is provided in the Java Collection Framework, our goal is to understand how it is constructed. So that is the focus of this video. So let's consider how an array list can be implemented. Although the underlying representation uses an array, the distinction is that unlike just using an actual array, which has a fixed size, an array list should be a dynamic data structure. To make it dynamic, it is necessary to ensure that when the array is full, a larger array twice the size is allocated and the old array is copied to it. By doubling the size, we minimize how often the copy operation is performed. What makes using an array as the underlying representation an ideal choice is that the get and set operations are very efficient because they involve an array access. Specifically, both execute in constant O of 1 time, which is the best performance possible. Adding or removing an element from the end of the list is also efficient. It too executes in constant time. Next, let's focus on some additional considerations related to the resizing operation. Resizing the array and recopying it too often would compromise the efficiency of the add operation, because that is the operation that increases the number of elements and can cause the array to become full. An amortized analysis is used to consider the cost of resizing and copying. When we amortize the cost of an operation, the cost is spread out over all add operations, since it is only done occasionally when no free space remains in the array. The Java Array class is implemented in a similar fashion, resizing and copying the underlying array when it becomes full. One minor difference is that the Java ArrayList class is a bit more conservative, allocating an array only 50% bigger. As we have done with every data structure implementation, let's now analyze the efficiency of each operation. Recall that the add method is overloaded, so we begin with the one that appends elements at the end. No shifting is required, so this operation is constant, O of 1. Keep in mind that we must also consider the resizing cost, but because it's being spread out over many calls, it will not be an appreciable addition. The other version of add involves inserting an element at a specified position. This operation will execute in linear time. The reason is that inserting elements requires that all elements beyond the insertion point must be right-shifted one position. When values are shifted to the right, the shifting must proceed from right to left, so as not to overwrite and propagate the same value. We have already encountered the need for right-shifting values in our example of a sorted collection. The removeAt method specifies the position of the element to be removed. The remove method specifies the element to remove. Both will execute in linear time. Much like inserting an element, removing an element requires a left shifting all elements to the right of the one removed. In contrast to a right shift, a left shift must proceed from left to right. The unsorted array collection contains a remove method that specifies the element to be removed, but it simply replaces the removed element with the last one in the list. That approach does not preserve the position of the elements, so it must be overridden so that once it locates the position of the element, it calls the remove method that shifts the elements. The get and set methods are given the position, which is just the array subscript. Accessing an array element can be done in constant time, so both operations are O of 1. The indexOf method calls the find method that it inherits from the unsorted array collection. It performs a linear search, so it executes in linear time. We are now ready to look at an example. This example makes use of the unsorted array list class. It is created as a subclass of the unsorted array collection because it is able to make direct use of the add method that appends elements at the end of the list and the find method that performs the linear search. As we have already seen, that class implements the collection interface. The unsorted array list class also implements the list interface, which contains all the methods that involve an index. And because list interface extends the built-in Java interface iterable, the list interface also requires that any class that implements it provide an iterator. The program example that uses the unsorted array list class is defined in the ArrayList GUI class. It will provide a GUI interface to test all the operations using an array list of integers. So let's run that and test out some of its operations. All right, so we're going to begin by appending several values, and keep in mind that what append does, it adds them to the end. And because this list is unsorted, the elements are going in exactly the order that they've come in at. So not in any kind of a sorted order. Okay, so let's try insert. And what insert does is it requires that we say what value we want to insert and where we want to put it. So let's put it at position 2. And remember, position start at 0, so position 2, this is 0, 1, 2 should be after the 21. And that's exactly where it was put. So let's insert one more, and this one, let's insert this one at the beginning of the list, which is at position 0. And we notice that that's exactly where it was inserted. All right, so let's now try the two remove operations. The first one is the remove at, and we specify which position we want removed. So that would be 0, 1, 2. So the 21 should be removed, and it was. The next is asking to remove a specific value. So let's pick one that's in the list, 56, and ask for it to be removed. Okay, now let's try get, and with get we ask for the position. So let's say ask for what's at position 2, and that should be an 8, which it is. Let's try a set. With set we specify the value to set and what position to set it at. So the 74 should replace the 93, which it does. Okay, and the find operation. And let's try first one that succeeds, which is 8. So it should tell us that that is at position 2, which it is. And now let's try to find one that's not in the list, like let's say a 34. There's no 34, so we should get a message that it's not in the list. And one more case to test here. What happens when we try to do something like an insert at a position that is outside the list? So let's try to insert a 37 at position 7, which clearly is not in the list. And we get an error message that the specified position is outside the array bounds. Now, the unsorted array list class is very similar to Java's array list. Java does not have an array list class that is maintained in sorted order, but because we already have a sorted array collection class, creating a subclass that is a sorted array list can be done with a minimum of additions. A remove at and get method must be added. An iterator is needed as well. All three will be identical to what was needed in the unsorted version. Unlike the unsorted array list, the remove method inherited from the sorted collection need not be overridden. It already shifts values. The one that was inherited by the unsorted version did no shifting. There are two operations in the list interface that cannot be supported. Both throw the unsupported operation exception, a predefined Java exception well suited for this purpose. The first is the add method that inserts a value at a specific position. The second is the set method that sets a value at a specified position. Allowing either operation could break the sorted order of the list, which is why they must be overridden.